wait a little bit. OK，那我就把这个 rigidity 这个东西的precise statement of this rigidity like rigorous write down. So this is like after like 20 years that people find that if the Bell inequality violates maximally, there exists basically it must be the Bell. So this is a theorem that called exact CHSH rigidity. Okay, so the statement basically say that if I have the set S, which is a state psi, and I have A and B, which is to be the d-dimensional strategy. So it's d-dimensional strategy. Let's say for this CHSH game. So remember that we talked about this game before that basically is 2 bits. So X and Y equals to A, X or B is the winning condition. So let's say, suppose I give you some strategy that for this CHS game such that it succeeds with the optimal quantum value. So succeeds with this optimal quantum value. So remember that we have these Bell inequalities, right? So we say that this quantum value is basically 1 plus square root of 2 divided by 2, or basically cosine square pi over 8. This is close to 85%. If you have a strategy which make this optimal, then there exists so-called isometry. So I will explain isometry. Basically, it's V from A to A1 tensor A2. So A is a vector space that Alice have, right? And another isometry called W from B to be B1 tensor B2, such that A1 and A2 are isomorphic. Sorry, A1 and A2 are isomorphic to this. Sorry, it's not A1. So it should be B1 isomorphic as a C qubit. And if we let theta to be V tensor W times this original state psi, then this theta will be the EPR pair. So basically it's a Bell state. Tensor some Young states. So psi, and this is A2, B2. And this is A1, B1. For some Young state. Fine. And there's a relationship. If V tensor W act on this A0, phi will just be Z. Act on the Z A1 act on theta. And also V tensor W B0, the state psi will be the ZB1 theta. And a similar relation is basically act on the X. X B1 theta. Okay, so this looks very complicated. So let me explain what the hell is going on. Right, so remember that we have like 2 parties, right? So let me just maybe use another board, right? So remember that we have Alice and Bob, and then we say that Alice can use A0 and A1 and B0 and B1, and let's say there's a state of, let's call it phi, which is a d-dimensional tensor product d-dimensional state, right? And we show that basically we already showed that the maximum winning probability is basically the Bell inequality, right? But what this theorem says that it's more stronger results. It says that if you can win this CHS game with the optimal value, then there exists the isometry such that you can map your original vector space to a larger one And then you can factor out the single qubits. Let's call it A1. And also there's another isometry, map the original B's, Hilbert space B, and map to the B1 tensor B2. And such that this A1 and B1, this A1 and B1, there are like single qubit states. And then you can factor your theta to be, you can just base transform, right? If you do the base change from this V tensor W to your original state, that state must can be written as an EPR, which is a Bell state tensor some Young state. So so remember that the all single Bell states can give you the optimal, right? So Alice and Bob can share arbitrarily other states, right? So I can have like 100 Bell state, but I only need one Bell state so that I can already achieve the maximum quantum value. And the moreover is this base change will make A0 to be Z, and make A1 to be X, and also make this B1 to be X on the Bob side, also Z, and the B0 to be Z. Sorry, is it correct? Yeah. Okay. So what this statement just say that in order to achieve the maximum value, the middle pair must, after base transform, the middle pair must be a Bell state, tensor some Young state. And there's no other degree of freedom for Alice and Bob. Alice and Bob can only do the Z and X measurement, the similar, or Z transform to X, similar measurement as we described yesterday. So this is called rigidity. And why the statement is so complicated? Because you need to make, because you can have extra states, right? You only need one Bell state to achieve the maximum, but you can have extra states. And Alice and Bob can do local unitary transform. So this is why this statement looks like so complicated. But ideally, it's basically you base change, there's a EPR pair, and you can do some tensor. And you must force this A0, A1, and B0 and B1 to be the same strategy. Okay, so let me just talk. Let me just recall the idea, so-called isometry. Right. So if you haven't seen about this isometry, isometry is like a general case of a unitary. So simply speaking, is that if you have a as I say Cn to Cm, let's say m is greater than n, and if you preserve the length, so preserve the length meaning that what? Let's say you preserve the length. So basically is that if A, just make sure that VA length is the same as A. And this is called isometry. So isometry you can view as a unitary but map to the larger space. So for example, if I have two-dimensional vector space, I can just embed into 3 dimensions. And this will be the isometry. Okay, so this is statement. And so what this statement tell me is that tell me that the states is unique. So to optimal, the states almost is unique up to the Young states. And also second is that what? The strategy is unique. So this gives you extra power, right? Because previously, if I win with higher than 75%, then I was convinced that Alice and Bob have quantum power. But I don't know which state between. But now if you can win 85%, then by this rigidity, then I was convinced that in the middle state must be Bell states, tensor some Young state. So this means that I can test the middle state. But this is much more powerful. So previously we just say I can test the entanglement because you win with higher 75%. But now if you win with 85%, then I can use this rigidity and make sure that the middle state must, after some base transformation, must be the Bell. Okay, so in order to do this, we need a 3-stage. So let me just write the proof. Proof is somehow like very long because this is the original some paper like 30 years ago, but we will like make it easy. So the first one we will show is anti-commutative. So we will try. Well, we will show that A0, A1 will be negative A1, A0. Okay, egg on side. If you reach the maximum, and also B0, B1 will be optimal, will be anti-commutative. So notice that when I write these two operators, right, in the beginning I didn't say anti-commute. You can do anything, right? And the second is after this, then we can use the previous so-called abstract QB that abstract QB lemma to extract this x and z. And the third that once we extract x and z, then we can extract the EPR pair or the Bell state. Okay. So the state is unique and strategy is unique. Okay. So step one, don't worry, everything is not it's difficult, but not so difficult. So let me just write C0 to be 1 over square root of 2, B0, B1, and the C1 to be 1 over square root of 2, B0 minus B1. Oh, just for the convenience. So remember, this is the standard Bell inequality. Right? This is the standard one. And I can write it as if I divide square, let's say. So let's say you reach the maximum, right? You reach the maximum, basically meaning that this guy is 2 square root of 2. And I can divide square root of 2 both sides to be here. And I can combine B0 and B1 and the B0 minus B1. So I can write this guy as a state psi A0 C0 plus A1 C1 psi equals to 2. Good. So we just replace B0 and B1 and the B0 minus B1 to be C0 and C1. Good. Good. Okay, my claim is that this equation indeed give you the anti-commutativity of A0 and A1. So my claim is that this equation indeed will force A0 and A1 to be anti-commutative on state side. Why this is true? Because we can use the Cauchy-Schwarz inequality. So let me just write it carefully. Right. So what we have is the this A0 C0 plus A1 C1. Oh, by the way, sometimes I will neglect the tensors, but you imagine that there is a tensor here. So A and C are A are first party, and C Alice is Bob side, and C is for Bob side. Okay, so I can just that I think V is a vector A0, let's say defined with A0 tensor identity. So identity just do nothing on side, and let's say W to be identity tensor C0 on side. Good. So this tell me that psi with A0 tensor C0 psi. By the way, this guy is what? This guy is just just the inner product with V and W, right? It's so obvious. So okay, so this is V and W, right? Oh, maybe it's yeah, because it's formation, so it's fine. So let's say you do this, and by Cauchy-Schwarz, right? These guys that's equal to square roots of VV and WW. Good. Cauchy-Schwarz, right? So meaning that is so what's VV? VV is A0 square. A0 square, right? So it's basically A0 square psi. And WW is identity square is identity, right? So it's C0 square. Good. And the A0 square is 1, as we just said, right? So I don't care about this term. I only care about C0 square. And the C0 is 1 over square root of 2 of B0, B1. So C0 squared is 1 over 2. And B0 plus B1 squared, B0 squared plus B1 squared is 2, right? So it's 2 plus anti-commutator of B0 and B1. So that means that this term I can write as square roots of identity, right? Because half times 2 is identity, right? So 1 plus 1 over 2 psi B0 B1 anti-commutation psi. Is it good? Good. Okay, so similarly, if I do like if I define let's say if I define V to be A1 tensor identity psi and W to be identity tensor C1 psi, I can do exactly the same calculation, right? So this same calculation will give me the psi of A1 tensor C1 psi, and exactly the whole calculation. The only difference is that so it will less or equal to this, which this is exactly the same calculation before. And then your A1 square is where is it? Okay, so your A1 square is identity, right? And then your C1 square, right? So the only thing you need to worry is this C1 square. So as you know, right, your C1 square will be exactly the same as this, but you change this. There's an extra minus sign between the commutator. Okay, so what this is 1 minus half of commutator. Okay, so now we have these two equations. It says that psi A0 C0 psi is square root less or equal to the square root of something. And also another equation is also less or equal to 1 minus square root of 1 minus half of something. But we say that there are sum to half, right? So let me just do this. Let's say I change let's see. Okay, let's say this guy, I call it alpha, and then this guy, let's call it alpha. Oh, sorry, it's near half is outside. Right, so what I got is that then let me just write in this. So this is the equation that we have, right? It's 2. But we say that it's less or equal to square root of half plus, let's say half alpha plus 1 minus alpha divided by 2, where alpha is just psi of B0, B1 psi. Right? It is, so I use Cauchy-Schwarz on both sides, and each one gives me 1 over square root of 2. Square root of 1 plus alpha divided by 2, where alpha is just this number. Okay, so now you can use your, so in like junior high school, right? There's a called arithmetic mean versus geometric mean inequality. So AM, GM, the equality, I think everyone knows, which A plus B divided by 2 is square root equals square root of AB. Is it everyone knows about this? Okay, so this means that these two guys, your 1 plus alpha divided by 2 square roots plus 1 minus alpha divided by 2 divided by 2, right, is greater or equal to 1 minus alpha squared. Let me see this. Let me say this. Divide by 4, right? So let me see how should I get this? Mm. So what I want to say is the following. What I want to say is that if you don't use this, if you directly solve this, is it? So what I want to say is that is it obviously that the only solution is alpha equals to 0? Is it obvious or probably it's not so obvious? But let's see. Is it so obvious? So what I want to say is that if you try to solve this red block equation, the only way to make it true is you just pick alpha to be 0. For the rest of okay, I think what why uh okay, so let's assume this is true. Okay, I will try to fix it. So if you directly solve this red block equation, then the only solution is alpha equals 0. I will come back and check this why this is true. Is it so obvious? Okay, so if you believe this is true, right? Because alpha equals 0 is then you reach reach 2. And what I'm saying is that if you take alpha to be like anything like I think you take anything which is greater than 0, then this guy will less than 2. Why it is true? Oh, I think okay. Let me do this. Let me do this. Oh, let me do this. So let's say I square this equation. So I get 4, that's equal to 2 plus 2 times 1 divided by this. Okay, right. Is it true? So that means this is 2, right? So that means that 1 is that's equal to 1 minus alpha squared divided by 4. Yes, so we proved that the only solution for this inequality is alpha equals to 0. Okay, nice. I mean, I'm okay. I'm stupid, but yeah. So alpha equals 0 is the only solution. But if alpha equals 0, meaning that these guys equal 0, meaning that B0 and B1 are anti-commutative on the state side, right? And by the symmetry that A0 and A1 are anti-commutative on the state side. Similar. Good. So that so we show that if you reach the maximum of 2 square root of 2, then all these 2 commutators must be anti-commutative. Right? So we prove it rigorously. Okay, so now we subject to the previous so remember there's a lemma that I talked yesterday, that if you have two matrices and they're anti-commutes, then we show that there exists a basis such that this guy is some qubits, some just a standard Pauli tensor the identity, and also this. Right, this is what we just showed yesterday. Okay, and we can. So this is the standard lemma, but we can somehow like generalize to the following. So it's like easy exercise, but you can check the following is true. If you use this lemma, let's say if psi is belongs to, let's say, n tensor B, and you have two operator A0 and A1 which acting on A, so such that you have two A0, A1 acting on A, and then they are all square one, and then they are commutative. Sorry, they are anti-commutative. Then okay, so the only difference in our previous lemma, what I just proved yesterday, and the below one, right? So the difference of this, so below one is just larger space, right? So it's easy to prove that you just change this unitary to isometry, right? So there exists an isometry V mapping to A1 tensor A2. A1 tensor A2 such that oh, by the way, this is band notation. So this A0 and A1 are operator. These should be curly A. This is band notation. I apologize. Okay, such that your V acting on the A0 tensor identity. So this is operator. Okay, acting on psi will just be the Z of acting on small A1 tensor some arbitrary guy, which let's say A2 and B. So this is V psi. And similarly, if you do you do X acting on small a. This is curly A1 tensor identity and the A2B sign. Okay, so if you feel weird that, let me just put it. So if you feel weird that the previous one is unitary, right? And this one is acting on a larger space A. Identity. So you look at each check and you just change this unitary to isometry. So you get D of A0 tensor identity and B dagger, right? This one is isometry, so you just need to move that B dagger to the right hand side. So what this theorem I proved yesterday to generalize it become like, since it's anti-symmetry, right? Basically we just show that you just generalize this to the isometry. So there is a B such that you actually there down this figure A1 looks like you just make a base change. You just make so this right have mean that I just do the base change, and after I do the base change, then I become the Z. And this I just know that if I use A0 and base change, then they are equal. So meaning that this A0 looks like Z after base change. And this A1 looks like X. Okay, so this is somehow like the small generalization, but you can easily prove. Okay, so if you believe what I say is true, then A0 and A1 and B0 and B1 now become X and Z, right? So the final question is that why the middle is the Bell pair? Why the middle is Bell pair, right? So because we just showed that A0 and A1, but why the middle is a Bell pair? So finally, we just need to extract. This is extract the EPR pair. Oh, so this is simple, right? So simple. Right. So remember that this relation that we just find, right? What this relation tell me is that this guy is true. 2 is right. So if alpha equals 0, then that's a quick. So if alpha is 0, then this 2 is actually equal to 1 plus 1. So that means that this term must be 1, and this term must be 1. Right? This A0, C1, C0 outside must be 1, right? But these are unitary vectors. Right? So this will make A0 and C0 act on the state side. It must be the same thing. So let me just say the words. So remember that identity, right? That identity will force this to be 1. Right? But this is the inner product between the A0 psi and the inner product with identity tensor C0 psi. But these are 2 unit vectors, and there are inner product is 1. So that means that they must be the same state. Okay, so that means that they must be the same state. This is the just simple results, right? And also A1. Right, so they must be, and it's easy to check that this also implies the anti-computation relation. Okay, so they are same state. So this is 1, right? This is 1. So this makes that also tell you that this A0 tensor C0 psi is psi. Because this A0 C0 is just another unitary, right? It can stay psi and inner product with the state size is 1. So that means that it must be 1, right? It must be the same states. Must be the same. Also, for A1 tensor C1 state side. Okay, so we can use the lemma, right? Now we can use the isometry to change this A0, C0. Okay. So what we do is just using our isometry, right? So we can use this isometry and acting on V on the A0 part and acting on W on the B part. So we just V tensor W acting on this A0, C0 side. And by definition, it becomes Z, right? It becomes Z. Acting on A1 and the small B1 part, right? It becomes Z. So A0 becomes Z and the C0 becomes another Z, right? So we get Z acting on a small A1, B1 and a V tensor W acting on the state side. This is the previous lemma that we just apply on A and apply on B. So it factors through for two small parts. But this equation is basically also equals to V tensor W side. Right? We just apply V tensor W on both sides. So this is our lemma. And this is trivial that we just do this. Okay, and similarly, we have the same equation for X. Let me just write here. So we have the same equation for X. We have the V tensor W acting on state side will give us XX, right? Because this equation, if I apply V tensor W on both sides, on A1 and C1 side, on A1 and C1 side will give us XX, right? So it gives X tensor X acting on the small A1 and B1. So small A1 and B1 are the lemma that factors through so we extract the small qubit, right? So the tensor W side. Okay, so finally, what we got? What we got is something, right? We say that V tensor W on state side is the stabilized by X tensor X and the Z tensor Z, right? So Z tensor Z will fix our states and the X tensor X will fix our state, right? So that means that our states. So finally, so that means that our states. So I just that theta to be V tensor W on our original state side. This theta is a property such that Z tensor Z on a small A1 B1 theta is the same as X tensor X acting on a small A1 B1. Theta is the same as theta. Okay. Now so it's trivial that theta is a Bell pair. So theta is a EPR pair. Tensor some Young state. Good. So finish it. So this proof, this is a complicated proof, but you can go home and think about it. Okay, so this is like after like 20 years ago that people show that this is called the exact rigidity. So simply speaking, it's up to base change. The middle states. And the strategy are fixed. And I think after like 10 years ago or something, there's in the 2000 there's a more robust results called the approximate rigidity. So I will just talk about statement, but I will not prove it because this is very difficult. This requires like more mathematical tool. There's an idea called approximate rigidity. Right, so remember that we say that if you get 2 square root of 2, that you get Bell state. But how about you get if you do a real experiments, right, you will not get 2 square root of 2 because square root of 2 is a fraction, is an irrational number. So if you do experiments, you can only get like 2 square root of 2 minus epsilon, some for small epsilon. So the question is that is if you can reach the 2 square root to minus epsilon, can you show that the middle states is very close to Bell states in the epsilon trace distance or any epsilon distance? Right. This is the question, that whether this exact rigidity can loosen to be so-called approximate rigidity. So theorem is almost the same. It says that if you have a strategy S set of size A and B, and you win with this CHSH game with the approximated, we say cosine squared pi over 8 minus epsilon for small enough epsilon. So there's this here should say there exists the epsilon greater than 0. Then I should say for epsilon greater than 0, but small enough. Then there exists the isometry, the same statement. A1 tensor A2, and the W is B mapping to B1 tensor B2, such that these A1 and B1 are small qubits. And if you let theta to be the same V tensor W acting on the state side, then the middle pair is close to the Bell state. So that means that the middle pair, if you take the EPR with some jump state, A1 and B1 tensor some state phi, this is some jump state, A2, B2. These inner products will less or equal to like O square root epsilon. So O mean, so big O notation, if you guys know. So it's some algorithm. So big O meaning that there is, okay, so let me just write up. So when somebody writes f of x is equal to O of g of x, this statement is saying that there exists a constant c greater than 0 such that f of x is less or equal to c of g of x for large x. If x is larger, we say, in the epsilon case, we basically meaning epsilon is small. So when epsilon is small enough, there is this constant that this guy is less or equal to the square root of epsilon. And moreover that you get a similar identity. So remember, for exact they are the same, right? But for the you can this states operator as a theta is less or equal to O of square root of epsilon, and there are 3 equations exactly the same. So this meaning that if someone play this CHS game, but with not the optimal value, but with the optimal value minus small epsilon, that you can prove that middle state is close to the EPR pair. So this is somehow like very like powerful results, because we are not just showing that optimal value, the Bell state give. So we showed. So what we show is the 3. Right? So there are 3 stages. The first stage that the quantum mechanics, usual quantum mechanics textbook will tell you that Bell states reach the max, right? So it's optimal in this CHS game. But second, we show this rigidity. What we show in this lecture is that the only state reach optimal is Bell up to this local base change. So this proof is if and only if. And third one, we also tell you that this is much more difficult. And I will not give the proof. Basically, there's an approximate version. Okay, so yeah, this is for today. And next week, we will start talking about quantum computation. So we finished the entanglement. So yeah. So we will go to like the complete new topics next week. And if you have any question that you can ask. Oh, by the way, you guys, is there anyone that needs to hand the homework to me? Oh, I posted a second homework, but it's not difficult. It's just some textbook paper. Yeah, 2 weeks.
我的思绪有点乱，
没关系，你就丢给我。
因为我提的话是按照顺序写的。
没关系，那我再整理。
我是有标题要，对，然后就是对。
OK，没问题，等我一下。